Uh, Hello, I'm Thomas from the University of Trondheim in Norway, and I'll be. Oh, you can't hear me? There we go. That's better. Yes. Thank you very much. I'll present our work on symmetry breaking and information flow in physical reservoir computing. So this is specifically related to the context of physical reservoir computing. And I'll be illustrating this through something we've just simply called lattice reservoirs in simulations. And so a bit of motivation first. Oh, shit. I have two computers and one of them has the speaker's notes, of course. Physical reservoir computing has become pretty popular in recent years. But one thing we wanted to look at is that the fact that physical reservoirs have physical constraints. And one of these constraints is that you have to embed the reservoir in space. And this comes with some limitations. For example, there's some inherent spatial coupling in a lot of substrates. This is basically just from the fact that there's an arrangement of constituent parts. This could be the atomical structure, or at a higher level, for example, decoupling of nanomagnets, which is what we work with. But there's not just the inherent embedded spacing for it. It's also, for example, for if you have a electrical circuit, there are wiring costs that could be relevant for this. And so on the slide here, I've added a few examples of physical reservoirs that are confined to a lattice or some sort of grid. And so we do our experiments by using an established model, the classical echo-state network, and then we impose some limitations on it. And we replace the reservoir weights with adjacency matrix of lattice topologies, which means that nodes are only connected to their nearest neighbors. There are no self-connections, and the lattices are not periodic. And the edges may be both undirected or directed, depending on the experiment. I will talk a bit about that later. But first, we try to benchmark one of these reservoirs, and we use the NARMA 10 benchmark. So it's a nonlinear autoregressive moving average, a very common benchmark. Oh, next slide again. And we see that these lattice reservoirs are not particularly good. The smaller reservoir sizes can be kind of okay, but as the reservoir size kind of grows, we can see that the echo-state network outperforms this pretty hard. And we also see that different types of lattices can be used, or we investigated different types of lattices. Here, square, hexagonal, and triangular. And we see that the particular type of lattice doesn't really matter that much. It's more the fact that it's a lattice structure, so their performance is kind of close. But it's a bit surprising that these reservoirs work at all, since they're so completely uniform. And we argue that the reason that they sort of work a little bit is that, one, there's some variation in the input weights, because you have an input weight scheme, and there are edges in the lattice. So along the edges, the nodes have fewer incident nodes. So you have a bit of reservoir diversity resulting from this. These undirected reservoirs perform pretty poorly. What do we do about this? What we thought could be interesting is that we see that the adjacency matrix of the lattice is symmetrical. So what if we break this symmetry? And we do this by going through all the edges in the reservoir and making them directed instead of bidirectional. And that's just a 50-50 coin toss. And we see immediately that this sort of restores performance in the reservoir. And we can even see that for the square lattice, we can almost compare to the echo-state network with the larger sizes. And that's sort of interesting in seeing that breaking this symmetry here is sort of allowing perhaps some flow of information within the reservoirs. And so we have these lattice reservoirs now. We've made them kind of work equivalently maybe to the echo-state network. And so we want to impose one more constraint, and we want to move away from a local wiring scheme where every node sees a different variation of the input signal. into just a global input scheme, which could be quite beneficial in a physical reservoir sense. And since we've seen that adding directedness to the reservoir sort of results in enough diversity for the reservoir to work, we also see that global input is not really detrimental to the network. Yeah, in fact, it actually improves it. And this was not at all the case with undirected reservoirs, in which case if you make the input completely global in an undirected reservoir, it's just completely detrimental. It doesn't work at all. And as an aside, the classical echo-state network doesn't really show a difference between a global or local input scheme. It's more important what to choose as your input scaling, for example, which is known in literature. And we believe this is quite promising in terms of physical reservoir computing and the fact that you can use simpler input schemes or global input schemes. I've added this table here to kind of illustrate the simplicity in that there are very few unique weights in the lattice reservoir. And we're by no means the first to create very simple reservoirs. The minimum complexity echo-state network, i.e. the ring topology, is very well known, presented by Rodan and Tino, and also further improved upon with skip jumps. So we're by no means the first to look at this, but we're kind of expanding the horizon here by adding lattice reservoirs as well, which could be kind of useful in terms of physical reservoir computing. Rings maybe harder to realize, maybe less space efficient, things like that. Yes, and I'll also return to the minimum complexity echo-state network here, because the echo-state network can be a bit hard to visualize, especially as you have more and more nodes. It can become completely incomprehensible once you have hundreds of nodes, because you need some sort of maybe spring model to try to visualize it. But the lattice reservoirs are very simple to visualize. So since they're simple to visualize, we kind of wondered, okay, can we maybe have a look at what the reservoir is doing? And what we ended up doing here was we start with a randomly generated lattice reservoir, and then we shrink it. And we do this exhaustive sort of greedy search where we evaluate the reservoir if we just remove some node, and then just remove the node that causes the least detriment to the performance. And that's what you see on the slide here. And we kind of see the interesting part, to me at least, is that we sort of converge towards a core stem, maybe a shorter memory, and that's augmented with some augmentative nodes. And I'd like to look at this as maybe we're converging towards a minimum complexity echo-state network, something kind of reminiscent of the cyclic reservoir with skip jumps. And this is one example where we sort of end up with just a delay line as we remove nodes, and you can see that there's a 0.4 error, normalized root mean squared error for evaluating that reservoir, which is exactly equivalent to what you get with an actual delay line. But you can also do the opposite. You can grow the lattice reservoirs. You can exhaustively search through all the places you can actually put a node and all the different types of edges you can add to a node and grow them. And performance gets a lot better when you do that. And we can also visualize it. Something interesting here is that holes seem to appear. There are parts of the reservoir where adding a node is detrimental no matter what you do. It doesn't matter what kind of edges you add. But it also gets a little bit more difficult to visualize exactly. You can't really find the core stem as easily just with the naked eye anymore. And it would be fun to sort of investigate this and maybe look for sources or sinks or some way of visualizing where the information is flowing in this network. And just to reiterate on this, building reservoir specialized for a task like we're sort of doing here, of course, outperforms the randomly generated one. And then finally, I'd like to talk a bit about reintroducing symmetry. So how much directedness is required? And it seems to be not that much. If you start with a network and then you just do this exhaustive search again, where you gradually make a node bidirectional again in a directed network, you can see that if you do this greedily and always choose the edge that causes the least detriment, you can have the reservoir be performant for quite a long time, and it doesn't really crumble entirely until you have maybe 90% of the edges be bidirectional. And this is quite promising in the sense that for physical reservoir computing, maybe only a minor breaking of the symmetries is necessary. And you need to do this to sort of facilitate a sort of informational flow in your network. Yep, that's it. Just quickly some conclusions. Physical reservoirs are subject to physical constraints, like spatial coupling, and that's prevalent in physical computing. Lattice reservoirs perform surprisingly well, but the edges seem to have to be directed to facilitate this information flow. We have to break their symmetry somehow. And then also global input schemes can be just as viable as local ones. So in some cases, only some slight breaking of symmetry is necessary.